Hi everyone. So in this presentation, we'll be looking at a concept that will keep coming up throughout the semester with regards to how we interpret and draw conclusions from data. And here's what we'll be focusing on today. Correlation does not equal causation. So let's dive into this. So what do we mean when we say that two variables are correlated? This just simply means that there is some kind of a relationship between these two variables. A change in one variable is associated with a change in another variable. So here in this example, you can see in this graph on the x-axis, you see time spent running, the time that a person spends running. On the y-axis, we see body fat. We can see a clear negative correlation between these two variables. For people who report that they spend more time running, they have less body fat. For people who report that they spend less time running, they have more body fat. So there's a clear correlation between these two variables. A change in one variable is associated with a change in another variable. Now let's take a look at an example where there's no correlation between two variables. So here we can see on the x-axis the shoe size that a person wears, and on the y-axis the number of movies that they've watched. Here you can see there's no correlation between these two variables. It sort of looks like somebody just threw some data points onto a scatter plot. The shoe size that a person wears does not correlate at all with the number of movies that they've watched. No correlation. Now if we go back to our first example where we said there was a negative correlation, can we say that the time that a person spends running actually has an effect? It causes the amount of body fat on that person. So running more causes a person to have less body fat? No, we absolutely cannot say that. Correlation does not equal causation. In order to make that claim, we would have to run a very large experiment that would control for a whole bunch of other variables. So for example, could it be that people who spend more time running also spend more time doing other exercises? Do they have more of a healthy diet than people who spend less time running? Are they younger? Are there socioeconomic factors involved, right? So there are a whole bunch of other variables that could be involved. So just because these two variables are related, they're correlated, that doesn't mean that we can identify a causal relationship, right? We'd have to do another experiment, which we'll talk about. Okay, let's look at another example. So here in this graph, I'm showing you how ice cream sales relate to polio rates. So these two variables are highly correlated. You can see that as one rises, so does the other, and as one falls, so does the other. Now, in 1949, doctors did not know a whole lot about polio, right? So they looked at a whole bunch of factors, and it does turn out that ice cream sales correlate very strongly with polio cases. Does this mean ice cream causes polio? Well, back in 1949, researchers honestly didn't know the answer to this question. We know now that, of course, ice cream does not cause polio, but I'd like you to stop and pause this video and think about what other factor could be relating these two variables. Okay, did you pause? Did you figure it out? So you probably guessed that it's temperature. So of course ice cream sales increase in warmer months and decrease in cooler months. And now we know that polio is much more easily spread in warmer temperatures than in cooler ones. So it actually makes a whole lot of sense that these two factors correlate. But can we say that there's a causal relationship? No, we know that ice cream does not cause polio. Okay, let's look at one more example. So here in this graph, you can see that the films that Nicolas Cage appeared in, the number of films that he appeared in, is actually strongly correlated with the number of people who drowned by falling into a pool. So this is a great example of how correlation does not equal causation. There is a relationship between these two variables, right? As one goes up, the other does. As one goes down, the other does. So there's a strong correlation. However, this is just by pure random chance, right? There's really no kind of, there's nothing linking these together like there was for the ice cream and the polio example where temperature linked those two variables together. Here, these two variables are correlating just by random chance. And if you want some amusement, you should Google spurious correlations. So this person, Tyler, vegan, he goes and just mines incredible amounts of data just to find random correlations. So I hope this really drives home the point that correlation does not equal causation. When we see two variables correlating, we can say that there may be a relationship there, right? But we can't say that one is causing the other. So correlation does not equal causation.